He's a USGS research ecologist. And we got, so he got his undergraduate at UC Irvine and his PhD at Cornell. Natural Southern Hardwoods. He's done over 30 years of research in Sierra Nevada. He's 3 handshakes removed from shaking hands with Abraham Lincoln.
It's true.
He knows to ask for beer in Zulu, which we can ask him in the post questions. And he's a principal investigator with the Western Mountain Initiative, where he works to understand and predict responses of Western mountain ecosystems to climate variability and change. So without further ado, if we could give a round of applause for Nate Stephenson.
Thank you. Good introduction. Thank you. So I want to, the origins of this talk, this is an experimental talk. I was looking at the lineup of this seminar series, and I noticed everyone was from a university who was speaking except me. And I thought a lot of you in the audience might want to have a different data point. You might be looking for careers in the future. And I'm an unusual data point because I've spent my entire career of 37 years in a small national park. Actually, the national park's pretty big. The research station in it is very small. And working very closely with land managers on the ground. And at any given moment, there's maybe 1 to 3 PhD scientists at that research station. And I found it really rewarding, and it's been a wonderful career. But like I said, this is sort of outside of my comfort zone, this talk I put together. So please bear with me. I hope it's good, and I hope it gives some of that feel of how it is to be at a research station like that. Can we douse the lights maybe so we can see better? So the roadmap, the first couple of sections are going to go very quick. Why and how I became a place-based scientist in a national park. Then the nature, I will talk a little bit about how I see the nature of the intersection of science policy and management. And then I go into some lessons from the intersection. And the first lesson, I probably wrote that wrong. The intersection is more complex, dynamic, and interesting than I certainly first imagined. And the way I'll get that idea across is just looking at the history of science and management in national parks and how that's evolved and how it's still evolving very rapidly. And even today, it's under a lot of flux and change. It's a real exciting time. Then, since the big deal these days are global changes, those are the big deals facing managers, there's this great desire on the part of land managers to have models of the future. What can I expect for the future? Where do I put my limited management funds on a landscape? I have learned that models have their limits, and they can help us think, but they aren't to the point yet that we can predict what's going to happen on a landscape out there, and we shouldn't pretend we can predict what's going to happen. We can use models to help us think, but not predict. But maybe we can use extreme events as previews of the future so that we have some sort of ability to say, hey, maybe this part of the landscape is more vulnerable than this part of the landscape. So that's the outline. Here's the place. Here's the Sierra Nevada of California. It's where I've spent my entire career, and I've been based here in Sequoia and Kings Canyon National Parks for 37 years. So why and how I became a place-based scientist? The why is really simple. I'm just madly in love with the Sierra Nevada. My family goes back 5 generations in the Sierra Nevada, and I've been really fortunate. My parents started taking me backpacking when I was 6 years old in the Sierra Nevada, and I knew it's where I wanted to be. This is the only part of this whole presentation where I'm going to shut up, but this is just so you can relate to why I'm in love with the place, these photos. And the people are a big part of it too. So you have these beautiful landscapes that attract a certain kind of people. And having people here, there's a good point. They would probably say they were able, so now I'm getting into the how did I get the job. They would probably say a similar thing to what I'm about to say. Luck and persistence, and it took both. Without one or the other, we wouldn't have made it. In my case, I had applied in 1979 through the normal channels to get a job in the national park, and never heard back from them because I was just one of hundreds of applicants. So I loaded up my 1965 Dodge Dart and withdrew the $60 I had from the bank and put it in my pocket, and I drove up and volunteered and got to know the people there. They got to know me, and eventually that led to a very low-paying job as a technician. But I was very persistent, and I said, okay, now I'm going to get a PhD. I'm going to do my PhD in the park. And that set me up for later. Anyway, to make a long story short, I ended up eventually becoming a scientist in the national park. And I had to go through sort of a postdoc period and all those sorts of things. But with persistence, this sort of thing can be done. So back to the why again, to me, this is paradise. But the other part of why is that there are snakes in paradise. We have these rapid global changes that have cascading effects throughout the ecosystems, like rapid climatic changes, altered fire regimes, air pollution, non-native invasive species. And I really would like to help pass on these wild places to future generations in as good shape as possible. So that's the other part of my passion of being there in the Sierra Nevada. So the nature of the intersection, this might seem naive, but this is how I view the intersection. Facts plus values equal action. Let me just go to the next one. Facts are the realms of, let me back up. If you don't have facts or if you don't have values, you can't act. If all you have is facts, they tell you the consequences of different actions, but they don't tell you what you want. And you can't get to where you want to go because you don't even know where you want to go. If you don't have facts, if all you have is values, you know what you want, but you have no information on how to get there. It takes the two of them together to manage wild areas. So facts are the realms of science. Values are often expressed in laws and policy, and there's usually wiggle room built into law and policy so that as societal desires change, you have some wiggle room. But law and policy put the sidebars or the sideboards on the values you're aiming for. And then action is management. And so one of the great lessons for me was how hard it is to be a manager because of these sideboards. Law and policy has court precedents and legal interpretations. And I can remember times when I've read a law like the Wilderness Act and thought I understood it and sat down with the manager and just said, oh, but this is simple, you just do this, this, this. And he rolls his eyes and says, look, Nate, there's a court precedent that says this is how you interpret this word in the law, and that's critical because that has these cascading effects. It's a lot more complex than I ever would have imagined. And on the management side, you have to legally comply with a whole array of laws that are layered on top of each other for a piece of land. Often, you have conflicting mandates for any given piece of land. There are social constraints. Law might say it's fine to go do a certain action, but society just says, no, we don't want you to do that. And then you always have to deal with staffing and funding. So it's a big, messy process. It can be frustrating because it's messy to get science into action, but it also can be very rewarding and fun at the same time. So in the National Park Service, I'm going to do my own paraphrase of this. The law that created the Park Service in 1916 basically said we have these beautiful natural areas. We want to allow people to use them today, but preserve them unimpaired for future generations. We want future generations to be able to look back and see more or less what we see today. And so I want to just now go through what is the history of how science has interacted with that set of values that is put forward in the Organic Act of the Park Service. I'm going to very simplistically break the history of the Park Service resource management into 3 periods. This is way too simple, but in a short talk you have to do that. I'm going to call the early period up through about 1963 the era of spectacles. Science didn't have a lot of effect on park management in this era. There were valiant efforts. There were some brilliant people who, like there was one, George Melendez Wright, comes out. He was an independently wealthy young man who thought science should be helping guide management in national parks. And so he started a little bit of a science program in the Park Service, but he died very young in a car crash, and it never really took off and had an effect. What was going on is the Park Service was very young, and the National Park management staff in Washington, D.C. realized they had to get a clientele. They had to build a clientele for the national parks for them to survive. You have to bring people in. You have to present people with something that's attractive that will get them there. And those were what the spectacles were. So I'm going to have some images like this where here's a natural resource manager here, and here's the target being aimed at. So the kinds of spectacles that happened were things like bison stampedes staged, feeding bears. This is in Sequoia National Park, and just look at all the little kids with their legs hanging over into the bear pit. You wouldn't get away with that today. Cut tunnels through trees. Staged firefalls. I don't know if you've all heard about the Yosemite firefall, but here's Glacier Point up here, and every night in the summer at 9 p.m., they would have created a big bonfire of red fir bark, and someone down in Curry Camp down here would, get the big audience gathered and shout up, "Let the fire fall!" And they would push all these embers over the edge. Now, these, except for cutting the hole in the giant sequoia, are pretty innocuous spectacles, and they serve their purpose of bringing in a lot of people to national parks. There were other things being done in the era of spectacles that were not so innocuous. Here's an example. It was policy to control predators in national parks. And you think about the law creating the national parks, and to me this seems to contradict it because it says preserve the wildlife therein, and that's obviously wildlife, but there was this idea that the public really wanted to see big herbivores, and if you got rid of the predators, there would be even more big herbivores that they could see. Well, it worked really, really well. In Yellowstone National Park is the most famous example where wolves were exterminated from Yellowstone National Park, and the elk populations just skyrocketed and started stripping the landscape bare. That was a big problem. Lesser known is that the same problem was happening in other national parks, like in Sequoia National Park. They put this deer exclosure here, and by the time 4 years had passed, all of these shrubs were stripped bare and dead, while the ones inside that were protected were still doing well. So, and actually the whole reason they created this deer exclosure was to help justify going out and shooting deer now. So first they went out and shot mountain lions, then they had to go out and shoot deer. So those are cascading effects. These were some of that era of spectacles changes that had effects that were not expected. Another really big one was that we removed fire as a predator. Fire was a natural part of a lot of these landscapes. And again, the idea was visitors don't want to see a charred landscape, so we have to keep fire out. And that had its own set of consequences. There were too many deer, but deer tend to eat conifers. They'll eat the broadleaf things. So you got very dense thickets of shade-tolerant species. Giant sequoias completely quit reproducing. There was no giant sequoia reproduction. And the risk of this kind of forest structure is a fire coming through, and these trees are low enough and dense enough you could get a crown fire in them that would conduct the fire way up into the crowns of the giant sequoia. So rather than just a little surface fire that would burn through here, you could actually start hurting giant sequoias. So through time, it was a combination of facts, science and values that started shifting things. And the facts had to do with what I just described to you, people realizing that removing the predators had been a bad idea, and maybe removing fire had been a bad idea. And at the lead of bringing about change was Starker Leopold here. I have to show this because my office mate thinks he looks like Antonio Banderas. And I'm just not I'm not as convinced as he is that there's a resemblance there. But a lot of this history is in a couple of really good books, Preserving Nature in the National Parks. This is from the 1990s. This book, Engineering Eden, is really new. It's from 2016, and they're very different books, but they give some of this history on this Leopold Revolution, what Starker Leopold got done. So now we're in the Leopold era, starting in 1963. And what had happened was the Secretary of Interior had asked Starker Leopold, who was a professor at Berkeley, to chair a panel to address the elk problem in Yellowstone that had been created by removing all the wolves there. And Starker Leopold couldn't help himself and his panel, the people who worked with him. They went well beyond that and gave a much more sweeping view of what national parks should be. And some of their key phrases were, this shows the era that was coming from, talking about the white man, but the condition, tried to restore the condition that prevailed in the area when it was first visited by the white man, and especially this one got a lot of attention. A national park should represent a vignette of primitive America. So what it was doing is turning your vision to the past. The past was the model for the future, so get things back the way they were and keep them there. And I think that era served us really, really well. It saw some changes, really huge changes that came about gradually, but reintroduction of fire was one of the huge ones, get fire back in the system, and reintroduction of predators. So this is a wolf being released at Yellowstone. And they've had, as far as I can tell, more or less the desired effects in getting things back to looking a little more like they used to. I got into the National Park Service in 1979, and I think it was the very end of the static management view of the Leopold era. These things aren't really well defined, but I do remember a discussion in my office where it was a serious discussion of, well, what's more appropriate? Should we restore to conditions as they were in 1875 or to conditions as they were in 1890? And that kind of precision was on some people's minds. So very soon after I got there, enough had changed in science to inform that maybe that's not appropriate to view a vignette of primitive America as a snapshot in time, but maybe a motion picture in time is more appropriate. There's a natural or historical range of variability in all ecosystems, and maybe that's what we should be aiming for. So a big part of my career early on was trying to help define this, what was now turning into a broader target, help define the historical range of variability of some of the forests, especially the giant sequoia groves, so we had a better idea of what things should look like after we reintroduce fire to try to get things back the way they used to look. The closing of the Leopold era, it's ongoing, I would say, realistically. That era is still embraced by a lot of people, but it's also in the process of being let go of by other people in the Park Service. I view it as largely a consequence of science and not of a shift in values. People would still really like national parks to look the way they did in the past. It's just that science is now telling us this may not be possible. So revisiting Leopold. There's a lot of words there, but one of the things that jumps out is no longer is it this idea of vignettes of primitive America is what we're aiming for, but actually we're aiming for ecological integrity. And so the shift is, it comes from the fact that science is telling us more and more, it's like we can't ignore it anymore, that the future is both unprecedented and unpredictable. And often I need the help of wise people from ancient times to articulate things. This is Heraclitus, ancient Greek, and here's what he said about the unprecedented future. And it's usually translated as there is nothing permanent except change. And I think if he were alive today, he would go farther and say, and the rate and magnitude of change that you face is unprecedented in human history. And this is the problem. The target's rapidly being forced out of bounds by environmental changes. This is going to be familiar to everybody, but I think it's worth looking at here. This is, I really like this figure because it shows today. Okay, this axis is temperature change. This one is time. We're over in the millions of years at the left side, and then we get into the hundreds of thousands of years. So it's kind of like a logarithmic scale. And by the time we're over here, we're in 50-year intervals. So there we are today. Weather records only go back into the 1800s, good weather records. We're as warm as we've been since the middle 1800s at least. The current interglacial, it's possible we're as warm as it's been during the entire interglacial, but that's less certain because the proxies used to reconstruct temperature have more uncertainty with them. And there's the ice ages. And what's I think is kind of remarkable is if you look at the difference between the coldest ice age temperatures and the temperature today, and then look at the projections for the next century, we could go through the equivalent of a Pleistocene to the present shift in temperatures. And that can really have huge cascading effects. This is a famous national park, probably how it looked in the Pleistocene. I don't think they had color film yet in the Pleistocene, but I had to fake it. So here's a sandy area, scrubby pines on it. Today, that's Everglades National Park with the big sawgrass prairies and the mangrove swamps. Another park as it looked in the Pleistocene, and then the warming, unveiled, what's today Sequoia National Park. One of my favorites here, here's a 600-foot deep freshwater lake. During the Pleistocene today, that's Death Valley National Park. So that amount of temperature change can have really profound effects. It's not necessarily a done deal. You know, there's a couple of things could happen. All the climate scientists are wrong. I'm not going to bank on that. I think that's such a minuscule probability that I'm going to ignore it. But we could, perhaps there's a technological revolution we don't know about around the corner that reduces our greenhouse gas emissions. Again, I don't think we should bank on that. We should assume that's probably not going to happen. I'd say more likely might be geoengineering, might be something we face as things get warm. The cheapest, most efficient way is probably to put particulates up into the stratosphere to reflect light. But that will have its own set of cascading effects. It might cool the average temperature of the globe, but it also, instead of direct beam radiation, you're now getting more diffuse beam radiation. It might change ocean currents. No matter what, climate will be changing in the future. Yeah, and even if it does a reasonable job of making climate a little more stable, we still face all these other unprecedented global changes like habitat fragmentation, pollution, and so on. So anyway, the bottom line is, no matter how you cut it, the future is highly likely to be unprecedented. So the problem then, we go back to, in a national park, what you would love to do is try to maintain things the way they looked, you know, a couple hundred years ago. That's the great desire. But in the face of these unprecedented changes, you're devoting more and more energy. It's as if you're Sisyphus rolling the ball up a slope, and the slope keeps getting steeper and steeper and steeper as you're rolling it. It's taking more and more energy to hold things in place or try to move them upward. And then at some point, you know, maybe that rock just no longer is stable, and it comes back on top of you and rolls down to the bottom. In other words, you've reached a threshold, and the fact that you've been trying to maintain certain conditions, they become inherently unstable under future conditions, and you sort of lose everything. And we've seen some examples of recent thresholds, like all the lodgepole pine die-off in the Rocky Mountains. And this one, Bandelier National Monument, they had actually put a great deal of effort into restoring some of their forests to a more sparser forest cover, using chainsaws in wilderness areas to get that done. And then it was just a fire of an intensity and severity that was out of bounds for anything experienced in historical times. It came along and slicked off all the forest cover. So that's the unprecedented. Here's the unpredictable future. We don't really know the target's exact path going into the future. A local example, because we're trying to plan for climate change in the southern Sierra Nevada, is, you know, here's different climate scenarios. There's temperature along this axis, precipitation change in percent along this axis. So temperature change might be relatively slow up to really rapid, and the models don't even agree, is it going to get wetter or is it going to get drier? And these would be really pretty different futures. You know, a huge increase in precipitation versus a really substantial decrease in precipitation. So we're not very good at knowing exactly where climate is going into the future. And then our biotic models, here's a couple of biotic models of US vegetation going into the future. These two different vegetation models were driven by the exact same climate scenario going into the future, and yet they give really different stories on what the future might look like. So you compound the uncertainty in the climate models with the uncertainty in the vegetation models, and you're left with even more uncertainty. And I will talk more about uncertainty later. But, and I'm bringing up this question because I've had people ask me, but how on earth can you plan and manage if you don't know what the future looks like? And we do have, there's several ways we can do that. We do have a lot of confidence in the directions of some of the changes, like we expect it to get warmer. We might be wrong, but that's the most likely direction things are going. We're all used to managing our personal lives with uncertainty in our lives, and that's why we do things like monitor for unexpected health changes. The equivalent would be, monitor your ecosystems for unexpected changes starting in them. We buy insurance against unexpected events. Maybe the equivalent, if you're a land manager, is if you have an endangered species that only has a couple of populations, try to establish some new ones out there, and we hedge our bets, like hedge retirement investments across an array of stocks and bonds. So maybe that means you don't do the exact same management strategy everywhere on the landscape, and you try different experimental approaches on different parts of the landscape. And there are well-developed tools like scenario planning that formalize these approaches. So if we can't have what the Leopold era wanted, which is retaining things within the historical range of variability, how do we interpret this preserved ecological integrity, which is sort of the new direction the Park Service is going now? Again, there's a lot of words there. There's actually a couple of paragraphs on ecological integrity in that report. I pulled out a couple here because they are the ones that resonate with me. Maintain regional native biodiversity, and I'll tell you why I underlined regional later, and maintain key ecosystem functions. It's worth looking at what's not in that definition. It's impossible to maintain the traditional idea of historical fidelity, and that's repeating what we've already said. It will be impossible to maintain natural biotic communities, and by that what I mean is the combinations of species we see today on the ground, because if there's any big lessons that come out of ecology and paleoecology, it's that most species act individualistically. So as the environment changes around them, this community will separate, and new communities, combinations of species that we're not used to, will come back together. And there's my version of an unnatural biotic community of the future. The pieces are still there, they're just arranged in a way that looks totally unnatural to us, but it's still a biotic community. So what is possible is a new notion of historical fidelity, and this is where I had underlined the maintain regional native biodiversity. That's all about parks being willing to, if you have a native species moving in from the south, native to the region, it may not be native to your park, you let the thing in. And if you have your own species in the park that's migrating to the north, you don't struggle to keep it in the park as long as it's going to be able to migrate north and still have a place it can live up north. So you're looking at a much broader scale outside the boundaries of the little land management units to be sure that on the big scale, native biodiversity is maintained as best as possible. And then maintain key ecosystem functions as best as possible. And even unnatural biotic communities ought to be able to do that if they maintain most of their key pieces, even if they might not be arranged in the same way they used to be arranged. So I look at these as possible goals. Maintain regional native biodiversity, maintain key ecosystem functions, and we can talk about strategies for getting there. And this, I'm going to go back to what it's like to work with land managers. These are all fresh ideas that are still being worked on, and what do they mean on the ground, and that's what makes it really exciting. But sometimes you hear of the 3 R's or the 5 R's. I have the 4 R's: restraint, resistance, resilience, and realignment. And I'll go through those possible strategies for attaining those goals. Restraint means just plain old leaving some areas alone and accepting the consequences of whatever happens. I have some people who are actually deeply bothered at the idea, who, when I suggest intervention, they're very bothered with the idea of intervention. And I realize after I talk with them, they picture us intervening over the entire landscape. And I think that's not going to happen for 2 reasons. One is we will strategically pick areas where we don't intervene as one of these bet hedging strategies. The other is a lot of these landscapes are so vast, we simply don't have the capacity to intervene in more than a few strategically chosen areas on the landscape. So a lot of the landscape is just going to suffer whatever consequences of environmental changes, and with luck, we'll be able to monitor it and maybe push it every once in a while. Resistance, I'm using resistance and resilience in the way that managers tend to use them and not in the strict engineering sense that is more common in a lot of the literature. But by resistance, I mean trying to resist the changes that are being imposed from the outside. We can do that for a while. Some examples, this one, here's someone irrigating a giant sequoia tree. You might irrigate a population of endangered plants, create fuel breaks to protect them, control an insect outbreak. Those are resistance strategies. Resilience, as it's most often used by land managers, is being sure you don't pass a point where the ecosystem flips into a whole new state. You want to be able to absorb those stresses without changing into a new state. And some of those approaches control a destabilizing invasive species. Really, if you're a forest person like I am, thin forests to maybe even more open than they were during historical times, but to give more water to the trees that remain and to make it harder for insects and pathogens to be transmitted. And finally, realignment is, we might actually try to facilitate change. And I think in the long run, it might be what we put most of our energy in. But in the meantime, resistance and resilience are short-term strategies to buy us time while we figure out the whole realignment thing. And some of the possibilities of realignment are mixing gene pools, which in the Park Service it makes people's skin crawl, because so much energy is put into, wow, this gene pool on this piece of ground is co-evolved with these conditions, and it has been co-evolved for centuries. We don't want to mess with that. But the reality is the environment's changing so rapidly, it's no longer adapted to that piece of ground. And maybe if we mix gene pools and let them sort themselves out, we'll have better adaptive capacity. What if you do lose your top predators, they go extinct? Your native top predators, should you consider bringing in a non-native top predator so that role is at least filled? And then the assisted species migration, it may not show, but here's a bunch of animals and plants on a bus. There's a buffalo right there. And they're getting ready to head north. And also, that's a really hard thing to think about in the National Park Service when so much energy has, until very recently, been put into keeping things looking the way they looked in the past. So realignment recognizes that change is inevitable, but that how it happens may not always be inevitable. So if we were managing for the historical range of variability, the environment is changing around us, but we're keeping things looking the way they look, you might get, I'm going to talk more about hotter drought later, you get a hotter drought that suddenly, here's your forest ecosystem services, it kills off almost everything, so you've lost most of your ecosystem services. One of the worst of these losses might even be soil down here, because that's some loss of biological potential if a lot of your soil erodes after this happens. And then maybe you go through a recovery period where a new species, either you bring it in or it comes in on its own, becomes established, but your ecosystem services are still relatively low. With realignment, you might consciously early on start shifting things, and you might start losing some ecosystem services at first. So you've thinned the native forest, you've brought in some species, native species from elsewhere that are better adapted to what you think is most likely for the future. Then you get your hotter drought, the big inciting factor, but maybe you don't lose everything. You've managed to ease it without this huge loss of ecosystem services, and you end up with the new kind of forest, but you get there sooner and having maintained habitat for old growth dependent species and things like that. So what's happening in land management agencies is the recognition that we've got to change things for the future. And managers have a great desire to have maps because they're always conducting triage. They never have enough funds to do everything that needs to get done. So what you do is you prioritize. You say, this piece of landscape, I think, is so vulnerable that putting money in it doesn't make any sense. So we're just going to let it go. This piece over here we think is really resilient, so let's ignore it for the time being. But there's this in-between zone where we might lose something unless we act now, and that's where we want to put our money. So there's a great desire to have detailed maps. This one was for the Southern Sierra Nevada, created to try to do some scenario exercises for how we might manage going into the future. But what is the proper role of such maps and modeling in general? I threw this in because I do think it is such a problem that it's so easy, relatively speaking, it's so easy to create a map like this, but if you only have one and you've only used one set of assumptions to create it, there's a huge risk that then you pass it off and it's taken as a reflection of reality. It's taken as the truth, a true prediction. So now we're getting into the models help us think but not necessarily predict. And again, I went to wiser people than I. Here's one of the greatest statisticians of the 20th century was George E.P. Box, and he says, all models are wrong, but some are useful. And I think that encapsulates it really well. And then one of the great physicists of the 20th century was Niels Bohr, and he says prediction is very difficult, especially about the future. And I agree wholeheartedly with both of those sentiments. So we had an opportunity. This hotter drought came to California, and I'll explain what a hotter drought is. Killed off a bunch of trees, so in hindsight, we can look at this piece of ground and say, this was a more vulnerable piece of ground, but look back here, things are greener back here. This was less vulnerable. And these are sort of the scales at which management happens. You can do a prescribed burn of a couple of 100 hectares and pull it off pretty well. So how good would vulnerability maps have been at predicting all of this? So first, what is the hotter drought? Drought has two components to it. One is the water supply component. When you have very low precipitation, you have a drought. That's the main component of droughts, but the flip side is evaporative demand. And the warmer the temperature, the more evaporative demand there is. So there's the supply and there's the demand side of a drought. And if this, I thought, was a very clever approach to explaining it by Park Williams and colleagues. The blue in the background, the blue squiggly line, this is a drought index, the Palmer Drought Severity Index. So down here is drought on the negative side, up here is the opposite of drought. The blue line is what the Palmer Drought Severity Index would be if temperature had been constant across the entire last century or so. It was maintained at the average through that entire time period. And so you would be about here, you'd be at about a -3 on the Palmer Drought Severity Index. The temperature effect pushed it down to -4. That's the orange line here. So this drought was unprecedented in the historical record, and it was unprecedented because of the higher temperatures. If it had only been rain and temperature had been constant, we would have equaled the 1924 drought, but as it is, it was much worse than the 1924 drought, and that's what's been killing off loads and loads of trees. But we completed this before the drought. It was another exercise in an attempt to be planning for climate change in the future, is a niche model for giant sequoia, mostly driven by climatic factors. So each dot there represents a pixel on a map that contains giant sequoias, and there's a principal component analysis that's mostly driven by climatic factors that says, aha, here is the climatic envelope for giant sequoia. And then it's driven forward by a GFDL scenario of the future, GFDL model under high greenhouse gas emissions. And you see some of the giant sequoia pixels on the landscape are migrating out of the climate envelope of giant sequoias. And by the time you're to 2099, most giant sequoias are outside of their climate envelope. So those little pixels go back onto a map, and you end up with a map like this. So here's Sequoia and Kings Canyon National Parks. Here's the sequoia groves. The red mean highly vulnerable. I'm being liberal with the use of the word vulnerable. This is actually an exposure map. Let's not get into the difference. Let's just call it vulnerability. Green is less vulnerable. Well, then this real-life hotter drought came along. So this is a scenario for a hotter, drier future. Then we got a little preview of a hotter, drier future with this severe drought. And something had happened that no one had ever recorded before, and that's that a whole bunch of sequoias showed dying foliage at a level that no one had ever seen before. And we managed to get people out on the trail. David was one of the people. I forget were you Erica? No, okay. And map how much foliage died back. And the reason these look like gummy worms is speed was of the essence, so people stuck to trails and were just looking at both sides of the trails and not doing cross country. So the warmer areas are where dieback was higher, the cooler colors are where it was lower. So now we are able to actually line up. This is just one grove. I think we surveyed 10 different groves. What was the predicted from that niche envelope model, that climate envelope model? How does that line up with what we actually observed of a response, a stress response of the giant sequoias to a warmer, drier piece of time? And the correlation was really, really bad. There's only about 4% of the variance was explained. So here's what the model had predicted, and here's what we actually observed in terms of foliage dieback. So this model really wouldn't have been that helpful to managers. They could have put a whole bunch of energy into these points over here, and they would have missed the most vulnerable parts of the landscape. And it doesn't surprise me that the model did poorly, and I'm going to try to go through why. Is you have to get all these things right for pixels. You have to get the physical environment right, and that takes, you have to get temperature, precipitation, snow dynamics, soil characteristics, subsurface hydrology. You have to get the vegetation right, and a really good vegetation map might be good 80% of the time. A worse one will be right a lot less than that. And then you have to have the right model that relates vegetation to the physical environment. And so I just want to pull out temperature to look at this really interesting study. They did downscaling of PRISM down to 30-meter scales on the landscape and set up weather stations at a whole bunch of places where they had those downscaled climate estimates. And they found a really high correlation between what was predicted, high correlation, what was predicted and what was observed. But that high correlation is just because if it's noon in the middle of August, the nearby weather station is going to say it's warm, and the weather station that's on that pixel and the one that's being driven by the distributed climate map is also going to say it's warm. That's not a very significant correlation, even though it's a high correlation. What's really important is the absolute error, and that was really high. So that means on average with these predictions of what was the temperature on this piece of land and what did the weather station there stay, 1.7 degrees Celsius. And to give a feel, at least in the Sierra Nevada, the average elevational range of a tree species dominance covers 2.6 degrees Celsius. So if you have these dots here, let's just say you predict that this little pixel is outside of the elevational tree. I'm not saying this well. Bottom line is the error is so big in temperature, it's wider than the distribution of a tree species along an elevational gradient. So we can expect lots of errors of omission and commission. And this is why I don't think we should be surprised. In my world here, so here's the giant sequoia groves, here's the Sequoia National Park, Kings Canyon National Park. There's only really 4 weather stations that go into the data stream that produces a downscaled climate. And they all have their quirks. And we're asking, this station and this station and this station to predict exactly what the temperature is right here, and also right here, and also right here. And here's one of the weather stations. So the temperature sensor is a point measurement inside this box here, and 20 miles away is another weather station with a point measurement of temperature. And we're asking them, we fit a model to them to tell us what the temperature is right here, and also another 20 miles off in the distance there. And it's just asking more than models could do. Because if you moved this temperature gauge, if you moved this thermometer 100 feet over, it would give you a different reading. And if you moved it over here, it would give you, move it anywhere, it will tell you something different. So this is not how you properly propagate error, but if you have a pixel and you have low certainty, or actually I'd call this moderate certainty. They're all above 0.5 in your temperature and your precipitation, snow, soils model. By the time you get to the end, you have very low confidence that you're right on all of those counts. So a related hazard, this was from a document to help for climate change planning in the southern Sierra Nevada. Here's the southern, so here's Sequoia National Park, Kings Canyon National Park, Yosemite National Park, and PRISM minimum temperature change was compared between this time period, 1911 to 1940, and 1971 to 2000. And so you can see some areas warmed, some areas cooled, and I should just ask you, does anything seem odd about this map? And this was in a peer-reviewed publication. Okay, that's a nearly 3 degrees Celsius increase. It's a nearly 30 miles away, 2 degrees Celsius decrease in temperature. But climate is a regionally coherent phenomenon. And you think about it and you go, what on earth could possibly be the mechanism that could drive a huge warming right here and very close by a huge cooling? I don't know of any mechanism could do that. Another thing going on, the glaciers in that area where it's supposed to be cooling down quite a bit have all been receding, and there was a chapter in this very large document that showed the time series of glaciers in that area as they receded, which implies that it's getting warmer. And also tree line has been advancing in that area, which also implies it's been getting warmer. So it's just wrong. And a lot of people use these time series of data, and the caveat emptor isn't blared loudly enough. They're highly sensitive to new weather stations being added or moved. And what happened in 1949 was a couple new weather stations were added in the Sierra Nevada. And so if you have a lapse rate that's been developed from 2 low elevation weather stations, and you use it to extrapolate up to what the temperature should be at very high elevation, and suddenly you add a new weather station, it could really shift that entire lapse rate line and suddenly cause it to appear there's been a great decrease in temperature at high elevation when actually there's been none. Does that make sense? And you can confirm that by, if you just look at individual weather station records, they do what you would expect because climate is a regionally coherent phenomenon. You have the temperatures going along, and when one station goes down, the other goes up through time, and they follow each other. There's a general warming trend, but when one goes down, the other goes down. When one goes up, the other goes up. So it's pretty clear that was a problem in the data. So the real risk is a manager could take a map like this and say, aha, this is a refugium. This area has cooled down, so we can expect things to happen more slowly there, and maybe this is a place we ignore for the time being while we focus on other areas. When in reality, the temperature change is fairly uniform across this entire region. Again, I just bring this out because, well, this explains it. There's really good news behind the reason I'm bringing this out, and that is our science does make a difference to management, and that's always really encouraging that this hard work we put in gets used by managers, especially if you sit down with them and work through it with them. But with that comes a huge burden of responsibility to be sure that you're not giving faulty information. So the caution is it's pretty easy to create a high precision map. So this, in a sense, is the holy grail. Oh my gosh, let's go here because that's red. That's where we put our energy right now in managing. But precision does not equal accuracy. And view that map as if it were a painting. Here's the Mona Lisa. And this is reality. Here's the inaccurate model of reality. And yet it's really highly detailed. You would look at that and see the vein bulging on the arm and all this kind of stuff and go, wow. The thing is, this is all we ever get to see. We never get to see the Mona Lisa. We don't know what it looks like. We just have this image. That is Michael Jackson, in case you were wondering. So precision does not equal accuracy. Compounding layers of uncertainty mean that at best model outputs are untested hypotheses. And But we can embrace that. I think we can embrace that uncertainty. We can use, especially if we have several different iterations of what the future might look like, use a map like this to say, well, let's start monitoring a couple of these areas and see if we're actually being any good at predicting what's going to happen there. In management, we can use bed hedging strategies, scenario planning. And I'm not at all saying we should abandon models. We just have to recognize them for what they are, that there are fictions, but they can be very useful fictions if we recognize that they're fiction. So we continue in parallel trying to improve our models, and that brings me up to the last thing I wanted to talk about, which is letting the ecosystems speak for themselves, because it really would be nice to have a vulnerability map that we had a good deal of confidence in, and that's where I'm hoping we can use extreme events as previews of the future. So, down to the last thing. I'm actually not going to go into very much detail. Oh, my time's almost up. This is perfect. We're trying to use the unprecedented hotter drought as our empirical preview of the future, and we're doing it this way. We have remote sensing by the Carnegie Airborne Observatory. We are at the same time monitoring tree populations and also leaf chemistry and physiology. I'm not a remote sensor, but it's really amazing what the Carnegie Airborne Observatory can do. It uses LiDAR to map individual tree crowns, and then it has hyperspectral imagery, 500 bands or something like that, that you can use to detect the chemical composition of each tree's crown, and you can use that to identify the tree species. So the ground tree population monitoring is mostly for calibration and validation, so every year we go back to tens of thousands of trees, and if one's died, we can tell Greg Asner, this tree died, and he can pick that image out, and we can say, and bark beetles killed it. And he can look at the change in the spectral qualities of the crown and see if it gave some hints that it was on its way to dying. We climbed a whole bunch of trees to get canopy foliage samples that then are analyzed for water content, nitrogen, water stress, non-structural carbohydrates, and so on. And just a real quick preview. In this image here, this is giant forest of Sequoia National Park. All of the light gray is forest canopy. And the Asner lab went through and picked out individual giant sequoias because they have their own spectral quality, so that's the colored dots, and then did integrated whole crown water content. And so the warm colors are crowns that had less water, the cool colors are the crowns that had more water in them. Make a long story short, it seems like there is some matchup. What's driving this gradient is these sequoias just have fewer leaves. They've dropped a bunch of leaves. It might be related to that foliage dieback we saw. We're still trying to work out all the details on this. So this might be some hint that we can get a map of giant sequoia vulnerability. The ones that drop the most foliage might be the more vulnerable areas. We don't know if this approach is going to work, and I hope I ought to be able to tell you in a few years. So coming full circle, I'm going to just go back and end on how and why I became a place-based scientist. This was the view from my office just a couple of weeks ago, and sometimes it's really nice. Thank you for your attention.
Any questions? I have a question.
Fire away.
I saw on the low elevation sequoia map you had that you have a bunch of better hydrated sequoias and blue ones.
Should we go back to that one?
Like moisture refuge that you were talking about earlier today?
Yeah, here we think this might be.
But even the lower you have a bunch of.
Oh, there's a couple of individuals down there these might be little moisture refugia where we think it's possible that water from higher elevation is coming down through bedrock cracks and coming out very locally. These are all things we're going to try to work out. We just don't know. But yeah, thanks for the question, David.
Yeah, since you're on that figure, I'm curious. You said that some of the trees might have fewer leaves. And I know when you look at thermal images of trees, the bark looks, when they're being illuminated by the sun, the bark looks very hot, the leaves look very cool because of evaporative cooling,
Right.
as long as they have enough water to
Yeah.
keep their stomata open. So is it possible that these trees that look warmer are actually more adapted just because they have, like you said, fewer leaves? Maybe
Yeah.
seeing more of the bark.
Well, this may address your question or comment is when you climb these trees, as UC Berkeley people have done from Todd Dawson's lab, Anthony Ambrose, and do pressure bomb them to see how much water stress they're under and do water content, you really can't tell a difference between these leaves and these leaves. So at the scale of individual leaves, they're staying well hydrated and happy. And so it was a response to the drought. I think of it as a smart response that those sequoias said, you know what, I'm starting to feel drought stressed. I'm going to drop a whole bunch of my leaves. I have less leaf area now, and that's going to maintain favorable water status. I don't know if that addressed your question because you did talk about temperature also and evaporative cooling.
Generally gets to it.
Yeah.
You talked about managing with like resistance and resilience. Do you think, and like biotic integrity, do you think biodiversity is like managing for biodiversity itself would be a resistance mechanism? Or even just, do you think it's worth managing for biodiversity's sake?
It may be both. I certainly think managing biodiversity for its own sake fits under the umbrella of what Park Service is all about. And there are probably people in this room better at, there's this eternal debate, are more diverse ecosystems more stable intrinsically? And I think it gets resolved. I don't study that myself. I think it's all resolved, and then I see a new paper come out that says no, and another one comes out that says yes, and so I don't know what the answer to that is. But left to me, I would say, a wise tinker keeps all the pieces, and I really doubt if a more diverse ecosystem is somehow becomes less stable, so why not maintain biodiversity? Yeah.
Kind of along those same lines, I suppose, when you've talked about in the future maintaining a regional species pool rather than at like a park level species pool, how do you envision working with other land management agencies? Because I could imagine that if you have a species moving out of your park, but you still want to ensure that it's in the regional area, you would have to work
Yeah.
with other agencies
Yeah,
or private landowners.
that's a really good question about how do you work with the adjacent land management units. And like these parks are surrounded by national forests, but the good news is they have to manage for climate change also. And those maps of the southern Sierra Nevada I was showing, they were developed because all of those different national forests and the national parks are all working together towards a common goal. They've all decided we need to address this together because it's too much to address as our own little isolated islands. So there are already individuals in those agencies who see that as a good thing and are moving in that direction. In other places, maybe not, I don't know, but I do know like Dave Peterson in the Forest Service in the Pacific Northwest in Seattle has put together a whole bunch of adaptation groups across the western United States that include parks and that include forests and probably even include BLM lands and Native American groups and on, and just gets these really diverse groups together trying to aim towards a common goal. They may not, within their own boundaries, have the exact same goal as everybody else, but on the broad scale, like this whole idea about, yeah, we want to maintain this species, and if it's going to migrate north, will you accept it? And then the other group says, yeah, we'll accept it.
One last question? All right, going once, going twice. That's it.
All right, thank you.